Hello, this is question 10 from the 2023 Step 2 paper, so the second of the mechanics questions. There's 5 parts to this question. I'll just put the first bit on this screen. There's quite a wordy question, so I'm just saving some space. But yeah, there's 5 parts. So this is part 1. We've got, in this question, the x and y axes are horizontal. Okay, so we've got a flat xy plane and the z axis is vertically upwards. Right, part 1, a particle P alpha, I think that is, subscript alpha, is projected from the origin with a speed u at an acute angle alpha above the positive x-axis. Right, so yeah, P alpha. Okay. The curve E is given by this. We've got a negative quadratic there. And y is 0. Right, so this is a parabola in the xz plane. Right, if E and the trajectory of P alpha touch exactly once, show that thing. And then we have to work out what A and B are. Right, so we've got 2 bits to this first part of the question then. So in this thing, we've got to show we've got U's, G's, A's, B's, and alphas. So we've got no Z's, no X's. Right, well, let's try and we've got this thing. I mean, this is one thing that we can use. That's one equation that's got A's and B's in. And then for the particle that's being projected from the origin with speed u at acute angle alpha. Right, so for this particle, so let's go for P alpha. We just do our general projectile equations of motion here. So x is going to be u times t times cos alpha. And our, well, not y, it's z now. Z is going upwards, isn't it? So that's going to be our u times t times sine alpha minus our gt squared over 2. Okay, so that's just our standard projectile stuff. We aren't going to be able to eliminate x's just by using these, are we? So we must have, what have I not got? Oh, here we go. Right, so E and the trajectory of P alpha touch exactly once, right? So that's the bit of information we're going to have to use. We're going to get some limiting case here, something to do with a discriminant with a double root. So if that's only happening once, it's going to happen once at a particular time. So if we can set up a quadratic in T and then look at the discriminant, there seems to be sensible way to go about it, because then that will get rid of x, z, and t, hopefully. So what have we got on all of this then? So we've got z, we need this z to be equal for both of them. So we're going to need that a minus bx squared is going to be equal to ut sine alpha minus gt squared over 2. Right, so I've still got this x, but I haven't used this yet, so that's going to get rid of that x, and then we've got rid of the x's and the z's. We've just got the t's, but yeah, if they're touching once, it has to be at one time, so that's fine. So I've got a minus b. Now x squared is u squared t squared cos squared alpha, and then I've got that is equal to u times t times sine alpha minus gt squared over 2. Okay, so let's get this into something which is looking more like a quadratic format. So let's go with b u squared cos squared alpha minus g over 2. That's the t squared bit. Essentially, I'm gathering this on the right hand side that I'm presenting as the left hand side. Then I've got a u sine alpha, that's the t, and then I've got a minus a, and that is all equal to 0. So this must have a double root for touch exactly once. Okay, so now we can jump into the discriminant and say our discriminant has got to be 0 for us to have our double root. So that means we've got to have u squared sine squared alpha, and then, well, it's going to be a plus because we've got a minus on the a, so plus 4a, and then the bu squared cos squared alpha minus g over 2. That's got to be equal to 0. Right, this is getting close to what we want, isn't it? It is close to what we want. Right, okay, we got rid of the sine squared and made it a 1 minus cos squared. Okay, so we've got a u squared minus u squared cos squared alpha plus, let's just expand this stuff out, 4ab, that's going to be a b u squared cos squared alpha minus 2ag is equal to 0. Right, I think this looks like it, doesn't it? I think they just rearrange it into the order they've got it in the question. So u squared minus 2ga is equal to, then yeah, I've got a u squared, that's going to be a 1. They put the cos squared alpha at the end. Then I've got a minus 4ab, yeah, and a cos squared alpha. Okay, excellent. Right, so that has shown that, so that's happy days. Then for the next bit, we've got E and the trajectory of P alpha touch exactly once for all alpha, with alpha is 0 to pi by 2, not inclusive. Write down the values of A and B in terms of U and G. Right, so we want this thing to hold regardless of what alpha is. Interesting, right? So we don't want this. I mean, this is a condition for these things to touch only once. So if we get, well, if we make this a 0 equals 0, because otherwise we're going to have this factor, this cos squared alpha kicking around, and we don't want it to depend upon alpha. So we're going to need, yeah, so we need to be independent of alpha. We need the coefficient of cos squared alpha to be 0, i.e. we've got 4ab equals 1, and that means therefore left hand side also equals 0, so we've got that u squared equals 2ga. So we've got a is equal to u squared over 2g, and then we've got b is equal to 1 over 4a. So that is 2g over u squared divided by 4. So that's g over 2u squared. Okay, so that's a and b. Is that what we wanted? To write down a and b in terms of u and g, which I've done. Right, okay, so that's part 1 done. Now move on to the new sheet for parts 2 and 3. Okay, so next part, we have an explosion takes place at the origin and results in a large number of particles being simultaneously projected with speed u in different directions. Okay, you may assume that all the particles move freely under gravity for t is greater than or equal to 0. Right, so we're in different directions. So before we had that u was an angle alpha above the x-axis, but now this could be any direction. It doesn't have to be above the x-axis, so we could be bringing y into play, so swinging this around horizontally, and we could also fire it downwards as well. We got an explosion, doesn't say we got any ground there. Describe a set of points which can be hit by particles from the explosion. Explain in your answer. Right, okay. This seems to be following on from what we had in the first part then. So what have we done in the first part? We've shown that we've got some curve, some parabola E. Okay, we've just been looking in the XZ plane, but we could say this in any horizontal direction, as in we could rotate that parabola around and it would still apply in that particular plane, that particular vertical plane. So that's fine. And we've shown that anything we fire is just going to brush against that parabola. So that's our limiting case. The thing that's bothering me here is we've got this limit. We've got this, that we've said that alpha is between 0 and pi over 2. But why have we had to say that? He didn't touch exactly once for all alpha. I mean, I've taken alpha out of this completely. I mean, we ended up with this thing. I haven't actually used that inequality at all for alpha that I can see. And if alpha was pi over 2, then we're just firing it straight up in the air. So we'd have that u squared was 2gz, which means that z max, so if we were firing it straight up in the air, our z max, our a, in this parabola would be u squared over 2g, which is what we've shown here. I don't really see why we've got this inequality. I mean, this is independent of alpha, so why would the range of alpha then be limited if it's independent of it? Okay, I don't know. I'm not really seeing why that's there, that particular thing, but I don't think it holds anything back on this. I mean, we're saying that we've got a, I'm not going to put this into words though. So let's put it over here. So in part 2, we've the parabola, i.e. this is, what do we do, it was curve E, wouldn't it? Curve E is the limiting case for a particle in the, well, xz plane. So therefore, if we rotate the well, this curve E about the z-axis, we get a surface which is the limiting case for all vertical planes. Okay, so therefore particles can hit, is that what I put? Hit, yes, hit, I use the word they use, any point inside or on this surface. Is that going to be enough? Explain your answer. Maybe say, I'll put in brackets maybe, if the if any point beyond the surface were hit, I mean that contradicts what we've just done in the previous part of the question. If any point beyond the surface were hit, then this contradicts finding of part 1. Okay, always difficult to stick these things into words, but I think that'll probably do. Right, part 3 then. Show that at a time t after the explosion, the particles will lie in a sphere whose centre and radius you should find. Okay, right, well, yeah, this is interesting. I mean, from a physics point of view, that's just obvious, I would say, because the particles will have moved ut relative to the centre of mass, and the centre of mass will have dropped minus gt squared over 2 in the z direction. So, but we can't give that as an answer in math. So what we need something which is more mathematical rather than just saying, well, this is what happens in physics. Even if you blow up something, the conservation of momentum, it's not changing where the center of mass is or how the center of mass is behaving. So even when you've exploded something into all of these different particles, you can still treat it as a whole system at the center of mass. So that means each particle will be traveling ut relative to the center of mass. Like I say, this isn't the answer I'm going to give because this is a physics answer. So that's going to be the radius of our sphere, and our center of mass, which is just starting at the origin, would have moved from rest in the z direction minus gt squared over 2. So what we're expecting to get is a sphere which is going to have that center and a ut radius. So that's the physics answer. Oops, radius ut. But we need something which is going to be more maths-like. So we want to have nothing to do with the angle in this. We just want to have, well, time in it, I suppose, because we're just looking at what is the position of all of the particles at a particular time. So we'll have to go back to our particle equations and, well, actually we can, what am I trying to eliminate? No, we want x. Actually, we want all of them, don't we? We want x, we want z, because that's going to give us the equation of our sphere. And we're going to want the time in it as well, because that's going to give us the radius. So, yeah, okay. So we're going to have, yeah, let's get these things together. So we had x was equal to ut cos alpha. So that's the x coordinate. We had that z is going to be equal to ut sine alpha minus gt squared over 2. So we want to turn this into something which is going to look sphere-like. So we're just looking in the xz plane at the moment. So that's going to be a circle, which we're then going to rotate about the z axis. So we want to turn this into a circle. So let's look at x squared and z squared, because that's what we're going to want in an equation of a circle. So x squared, u squared, t squared, cos squared alpha. And then z squared, well, we want to do z plus gt squared over 2 squared is u squared. I mean, you can see that's already getting at our center of the sphere here. That's our z coordinate. So if we add these things together, we're going to get x squared plus z plus gt squared over 2 squared is equal to, we've got sine squared plus cos squared, so u squared t squared. So that is a circle, center 0 minus gt squared over 2, radius ut, and then rotate this about the z-axis. So we've got it moved. So we've got a three-dimensional. We've got a volume rather than just a circle. Then about z-axis to get sphere. Obviously, the sphere is going to have the same radius as the circle, and it's going to have the same center, but we're now bringing in the y coordinate as well. So yeah, I've run out of space on the screen, but essentially I'll be then writing this bit as being the final answer. Okay, right, so that was one there. Yeah, really that was a question for the physicists, i.e. me, rather than going through the maths, but the maths wasn't too bad for figuring out that last bit. So yeah, okay, that was fine. So we got 2 bits to go, parts 4 and 5 on the last screen. All right, so on the home stretch here, part 4, another particle Q is projected horizontally from the point 0, 0A. Okay, so the peak of curve E with speed u in the positive x direction. Show that at all times Q lies on the curve E. Okay, well that should be straightforward, shouldn't it? It seems like a short part of the question compared to the others. So it's been projected with speed u in the positive x direction. So x is going to be u times t. That's not going to be changing. And then we're going to have that z is going to be, well, we're starting at a, and then we're taking off gt squared over 2. So we could say that that is a minus, well, t squared is x squared over u squared, so gx squared over 2u squared. And what did we have before? What was it? That was a minus bx. Let's go back to the, where's sheet 1? So yeah, we want a minus bx squared, and b is g over 2u squared. G over 2u squared, yeah, which is a minus bx squared, which is curve E. Okay, right, so that was pretty quick. And then the last part then, so part 5, show that for particles Q and P alpha to collide, Q must be projected a time that after the explosion. Wow, okay. So Q is always on that curve. It's always on curve E. We know that P just touches that curve. So, because we did that in part 1, and that's at a specific time. So we can say how long it takes for P to get to the curve E. Now, Q doesn't necessarily have to be there. Well, it has to be there at that time, but it doesn't immediately tell us. Q's not at all points at all times, is what I'm trying to get at here. So it's not just the case of, well, how long does it take P to get to Q? We have to factor how long Q will take to move along the curve. So let's go back though to from part 1, because this is clearly, I would say, coming from this. We had an equation that we used. Which one am I thinking of? I'm thinking of probably this one. Is it? Is this the one that I want? Yeah, this looks. Yeah. Don't know actually. Do I want that one? Well, this is just rearranged, so that's probably. I mean that. Yeah, that's the same thing. I've got to have T in it. I mean, T's disappeared from these ones, so it's going to have to be this thing here, isn't it? So, gosh, it's a mess. Right, I'm going to have to make it. I'll write this down on a bit of paper and then come back and. Okay, so copying across that. So that equation there, putting in what A and B are, I've got GT squared cos squared alpha over 2 minus GT squared over 2 plus TU sine alpha minus U squared over 2G equals 0. So yeah, that is just taking this thing here, this equation, and putting in what B and A are. So once I put those in, I end up getting this. Okay, so that's telling us the time that it takes. We're going to be able to, what am I going to be able to do with this? I want to tidy it up a little bit. Yeah, I mean, I suppose I can get rid of, if I do a cos squared is 1 minus sine squared, those GT squareds are going to disappear a bit, aren't they? Because I'm going to, yeah, they'll just cancel with each other. So that is going to be, and then I'll move everything to the right hand, well, multiply everything by -1. So this is going to be a GT squared sine squared alpha over 2. Then I'll have a minus TU sine alpha. Then it will be a plus U squared over 2G. So yeah, that's doing a 1 minus sine squared, cancelling those GT squareds over 2, yeah, multiplying by -1. Okay, so I've got that. Then, well, let's get it all on the flat. That's always quite nice. So let's multiply everything by 2, multiply everything by G. So that'll be a squared there. And then I need a G in here. So I've now got G squared T squared sine squared alpha minus 2G TU sine alpha plus U squared is equal to 0. So let's get what T is then. So T is going to be a 2GU sine alpha. Then, well, this must have a 0 discriminant because that's what we were doing before. We've shown that it's got a 0 discriminant. That's definitely right, isn't it? Because we'll have a 4G squared U squared sine squared alpha and a 4G squared U squared sine squared alpha. Yeah, so that is 0. And then we'll have a 2G squared sine squared alpha. So that is, cancel that, that and that, that and that. So we've got U over G sine alpha. So that is how long it takes for P to get to E. Right, so that's step 1 on all of this. But then we have to say where, well, we have to get Q to the same point for them to collide. So let's say for some delay, because this is what we want to work out, we need the delay that Q has got. So let's say T subscript D for the delay. So Q will have travelled for t minus td. So therefore the qx coordinate, so let's just say in bracket the x coordinate, will be the same as p, and it's also going to be u times t minus td, and same as p, well, p alpha, because otherwise they won't be colliding. So I've got that u t minus td is equal to u cos alpha times t. So we get rid of those, and we know what the time is because that's when p gets there. So it's this t. So I've got that u over g sine alpha is equal to u over g sine alpha times cos alpha plus td. So td is going to be u over g sine alpha 1 minus cos alpha, which is what we've got. Excellent. Right, okay, so that was not too bad. That was a fiddly question. I quite like it though. I think some parts were certainly easier than others. If we go back, the beginning wasn't that bad. I think that part 1, and that was quite a lot of work, so I expect there were quite a few marks for that part 1. But that was okay. I've still got this slight, question hanging over why they've put this on, why they've put this inequality. If you've got any ideas about that, then let me know, because that didn't seem to really feature in this at all. So I don't know, maybe you've got some ideas on that. But that aside, that first part was fine. Then the second part, yeah, okay, the second part, I mean, that was, it's awkward putting some of those things into words, but I don't think that was too bad. Part 3 was, yeah, that was fairly straightforward. A little bit shame you can't just go with a physics approach, but that's maths for you, isn't it? But that wasn't too bad. And then 4 was probably the easiest part, I would say. And part 5, yeah, it wasn't too bad. I mean, you had to sort of conceptually come up with what's going on, as in Q's moving along some path, P gets to the path at a particular point. So we just have to get the time delay so they're meeting in the same place. But yeah, all in all, that was quite a nice question, I would say. I think it was maybe slightly more difficult than question 9 out of the 2 mechanics questions. Question 9 was a bit more standard maybe for resolving forces and going through our equations of motion and things like that. This one had a little bit more conceptual understanding we had to deal with, but I like that question. I think that was quite a good one.